Okay, so we're going to take a look at a much more complicated problem this time. It's the sort of thing that you want to keep track of. We're going to deal with two billiard balls, and we're going to deal with conservation of momentum in 2 dimensions. Okay? So I'm going to start off. I'll draw this out, and then we'll switch over to another slide so that we can go back to our picture as needed. I've got a red billiard ball here, possibly a 3-ball, and it is going to collide with a blue one. I'm going off of memory here. Is that a 2 or a 4? I can't remember which one's purple. But use your imagination. They're 2 billiard balls. We're going to say that they are both identical, that the mass of the blue one is going to be 150 grams, and that the mass of the red one is also 150 grams. Okay? We've got a situation where I'm going to say that our initial velocity for the red one is going to be equal to, what is my value? 2.5 meters per second, and I'm going to make that straight up. I'm going to make this my positive y direction, and this my positive x direction. Okay? So starting off, this guy is straight up in the y direction. I'm going to have him moving straight up. Okay? My initial velocity for my blue one is going to be 0 meters per second. It's just sitting there. It won't know what hit it. So technically, if I'm going to describe this vector here, I would have 2.5 meters per second at 90 degrees, because it makes a 90-degree angle with the x-axis. Okay? So it's going to be straight up. I'm going to have a situation where this ball, the red one, is going to come up and hit the blue one, and they're going to go off at an angle like this. They're going to go off at the 2 angles. Can I actually grab and drag 2 things at once? I didn't think so. Smartboard technology can do so much, and yet some limitations. I'm hoping to get a real-world video of this so that you've got an idea of what's going on. But in this case, we're going to have a situation where this guy goes off this direction, and the blue guy goes off in that direction. Now I'll tell you this, that our final velocity for the red is going to be equal to, strangely enough, where's it at? 3 meters per second at 30 degrees. Now that may seem very strange starting off, that hey, somehow it's moving faster than it was before. But we're going to see how that works out with our vectors. Remember, this is not 3 meters per second straight up like this was with 2.5 meters per second. This is 3 meters per second. Oh, I've drawn this wrong. I apologize. In this case, it's going to be like this. I apologize. So the red one goes off this way, and the blue one goes off this way. May seem strange, but we're going to see how that actually works out. All right, so in this situation, we're going to go through, and I'm going to say that we're ignoring friction or anything like that. We are going to check to see if we have any significant external forces, and I'm going to tell you that we have no significant external forces, which means we have conservation of energy. And conservation, as I've said many times before, means what we start with, we end with. Now here's where things are going to get a little difficult, or a little bit different. Again, we could take a look and we could start off with, hey, our momentum initial for our red one plus our initial momentum for our blue one. And that's going to be the momentum that we start with, right? So if I plug in my values for initial, I've got my first one started off at 2.5 meters per second, and it has a mass of 0.15 kilograms. Look at that conversion to useful units. Take that, grams. Plus. Well, I could fill this in, but we know that it's going to be 0 meters per second times 0.15 kilograms. That part's going to go to 0. Notice, though, our vector sign. I've mentioned it before, and it's going to come into play now, because we've got more than one dimension that we're dealing with. We started off with all of our momentum in the y direction, at 90 degrees with the horizontal, with the x direction, okay? In the classic way of defining vectors. What we end with, however, in this case is, we have our momentum final, which equals, we said 3 meters per second at 30 degrees. Okay, well, let's take a look at that. We've got a vector where it's going off like this. This angle is 30 degrees with the x-axis. We know that the total length of this is 3 meters per second. All right, so vectors. I knew they'd come back, and indeed they have. So we've got a triangle here. It's a right triangle because we're using a coordinate axis that has 90 degrees between our x and y, which is good. And so we've got a situation where the total length, our hypotenuse, is 3 meters per second. I could see that this is the opposite side. This is hypotenuse, so I would apply. So sine of 30 degrees equals my opposite side, which is going to be my momentum in the y direction, and this is going to be my momentum in the x direction. Okay, so this is my momentum in the y divided by 3 meters per second. I'm going to multiply, or I'm sorry, that's not momentum, that's actually going to be my velocity. I apologize on that. I would multiply this by 0.15 kilograms. 0.15 kilograms. Now that's my actual momentum. Okay, I'm going to multiply this by 3 meters per second times 0.15 kilograms, running out of space. I'm going to do the same thing over here, because I have to do the same thing to both sides. And I will end up with that my momentum in the y is equal to, let me double check here, should be, yes, 1.5 times 0.15 equals 0.225 kilogram meter per second. That's how much momentum I have in the y direction. My momentum in the x direction, if I solve for that, I'm going to find is 0.39 kilogram meter per second. All right, so we know, let's take this by the numbers. We've got a y direction and an x direction. How do we deal with vectors? We split things up into x and y, which we've done here, and then we can actually start doing our addition. So we started off, let's take a look in the x direction. We started off with an initial velocity or momentum in the x direction for the red guy, which was, well, where was all of our velocity? It was all in the y. It was straight up at 90 degrees, 2.5 meters per second. So we actually started off with our initial, we had 0 meters per second times the mass, which is 0.15 kilograms. Okay, and then we also had momentum in the x at the beginning for the blue was 0 meters per second times 0.15 kilograms. All right. So we started off with, in the x direction, our total momentum equaled 0 kilogram meter per second. This is our initial conditions. We add those together and we find that we ended up with a whole lot of 0 in the x direction. Let me mark that. Okay. Well, let's look in the y direction. Well, in the y direction, that's a little bit different. We started off with, let's see, we had our initial momentum in the y direction of this guy was 2.5 meters per second times 0.15 kilograms. For blue, we had in the y, still 0 meters per second because it wasn't moving, times 0.15 kilograms. So that guy's 0. So we would just have 2.5 times 0.15. We started off with a total of our momentum let me write that in black to keep with what we're doing. Our total momentum at the beginning was equal to, in the y. Let me erase that vector because I've marked it, but it's in the y. Comes up to 0.375 kilogram meter per second. All right, so we've got a situation where now we know that initially, start with, in the x direction, we had 0 kilogram meter per second squared, right? We found our initial ones, and our initial in the x is 0. In the y, we had 0.375 kilogram meter per second. Let me double check that. That's what we started off with in the y direction. Okay, so what we start with, we end with, right? And we found that for our red guy, red ball, we ended with 0.39 kilogram meter per second. And in the y, we had, 0.225. All right. So, well, in the x we started with 0. So we would have 0, that's my initial, equals what I ended with in the x, 0.39 kilogram meter per second. For my red, well, we're trying to find out what happened to the blue guy. He's going off to the left, which is good, because we're going to find that 0 equals 0.39 plus our momentum in the x direction for our blue guy. Quickly solving that, I find that my momentum in the x direction for the blue guy is going to be equal to negative 0.39 kilogram meter per second. That negative means that it's moving to the left, which is good because we expect it to move to the left. All right, I need to mark that this is final. So this is what we start with, this is what we end with. Okay, let's do the same thing in the y direction. What we started with was we had a total amount of 0.375 kilogram meter per second, as I recall. We're going to set that, it was all coming from the red. We now have a situation where we've got 0.225 kilogram meter per second plus whatever's going on in the y direction for the blue guy. Okay, well, some quick math, and we can find that our momentum in the y direction equals minus 0.225, 0.15 kilogram meter per second. Now that we've got this, our x component and our y component, we can find out exactly where this guy's going. So, we've got a situation where we had a negative in the x direction. Let me find that. Negative 0.39. So that's 0.39 kilogram meter per second. All right. I took care of that negative by pointing it to the left. And this is going up by 0.15 kilogram meter per second. And my resulting vector is like this. Well, I just solved that triangle. And I will find that I should come up with something along the lines of, it should be 0.42 kilogram meter per second. And this angle comes up to, should be just about 21 degrees. We can also find our final velocity, because this is our final momentum total for our blue guy. We can find that our final momentum equals our mass times our final velocity. And solving for that, I can find that my final velocity velocity should come up to 2.8 meters per second. The important thing to remember about this, it's complicated and it's kind of a pain, but it all comes down to the same things that we've run into before. If there are no significant external forces, momentum is conserved. Okay? Conserved means what you start with, you end with. Unlike energy, this is a little more complicated because energy, which was our other conservation that we've dealt with, was a scalar. It did not have vector along with it. It didn't have directions, I should say. And so what's changed in momentum is we have to conserve momentum in given directions. We have to conserve what's in the x, what we start with in the x, we end with in the x. Start with in the x, we end with in the x. So we started with 0, and our red here at the end had 0.39. That means that our blue had to have negative 0.39, so that they would add together to be 0, to stay with what we started with. We started with this much in the y. Well, we found that this plus this is equal to what we started with in the y, and that's what we ended with in the y. It's still applying the same thing. What you start with is what you end with. But now with momentum, we have to keep track of these in each of the dimensions. In the x dimension, in the y dimension, and you can even do this in 3 dimensions by having the z dimension as well, the z direction. Okay? It's a bit more complicated, but this is precisely how you do it. It's exactly the same things we've seen before. You start with, you end with. And this time, all we have to do is solve some triangles to find out what's happening in the x and what's happening in the y. As long as they're at a right angle to one another, they don't affect one another. Okay?